Okay, so is it full screen? Okay, so good evening to all. Today is the sixth week. We are discussing about spectroscopy and characterization of different polymers, elastomers, and composites. It's already taught by Professor Santanu Chattopadhyay, and here myself, Samaresh Ghosh from IIT Roorkee. As a TS student, I am here. So today we will discuss mainly two different spectroscopic techniques. So till now we have discussed about FAR. We have also discussed UVVs, and today we will discuss about photoacoustic Fourier transform infrared spectroscopy, and then another very important is Raman spectroscopy. So first we will start from photoacoustic FTR spectroscopy or PAS. So first, why the PAS differs from FTR? So we'll next slide we'll discuss about the basic principle and instrumentation. Before that, just uh, to make a difference between infrared and PAS, basically it is a emission rather than the absorption technique, and also it is very versatile and also required a very small amount of sample to do the analysis. And the most important thing is PAS can do both qualitative and quantitative analysis, and also possible for both surface and depth profiling. That is little bit difficult if you go for the FTL. Now why it is difficult we will discuss in later section. So from the instrumentation part, so there is a source of radiation. So you may use IR, you may use UV. Now we are discussing here basically IR. That's why it is photoacoustic Fourier transform infrared. If you use the UV, it will be passive UV, just like that. So there is a radiation source, there is a chopper. It is nothing but a device that is rotating, and in that way it is modulating the radiation frequency. So it is not continuously the radiation continuously reach up to the sample. So it is sometimes it is blocking. So in a particular frequency it is blocking, and then it is passing through the IR radiation to the sample. There is mirror, and also you need a inert gas. Why it is helium? We will discuss it later. And here is the sample. So through this the sample is irradiated with the radiation. After interacting with the radiation, the sample will heated up, and that heat ultimately will be detected with a detector. So, and why it is acoustic? That is because when that radiation is coming to the sample, so that sample molecule are interacting with the radiation. So there is a chance of a development of heat when it is colliding with the radiation. Radiation means basically that is a photon. So when that photon is making a collision with the sample, it is generating heat. That heat will come through the, here is the gas helium, through the gas that will generate a acoustic wave. So since this is not continuous, so when the heat is generating and when it is blocking the radiation, so first it is generating, it is colliding, it is interacting, and in the next phase it is not interacting because this chopper is blocking the radiation. So how it is working? So when it is interacting, it is generating the heat. That heat will come through that helium, so it is detected, and subsequently next phase, when there is no generation of heat, so again there is a rarefication of the gases. So that's why it is like a wave is generating, that is an acoustic type nature. That's why it is called the PAS, photoacoustic. Photon is coming, and then it is generating the wave like a acoustic wave. This is the main fundamental thing. Now the excited molecules gives up that excess energy, what I have already told you, that when it is irradiating, it is generating the energy, and that energy actually emitting as a heat energy. And that heat diffused to the surface of the sample, and it create pressure wave or acoustic wave. How it is creating? Because there is a helium. That heat will generate that wave, and that wave is detected by a detector. If you use microphone, it will catch the sound. That's why it's a acoustic wave. And you may use also piezo type material as a detector that can also respond with the heat. Now next, as I have told you why it is helium, you may also go for the nitrogen atmosphere. That is also inert. That means you need a gaseous uh, environment. That gas should not be absorb that radiation. So the gas first of all should be inert and it should not absorb the radiation. And another thing, if there is a very small amount of heat is generating, still that small amount should be sensitized the gases. So since helium is a very high sensitivity due to its very high thermal conductivity and also it has very low heat capacity, that's why the most preferred gas is the helium. Now the samples to be analyzed. So why is the novelty in case of gas? You may also use a seed sample. You may use also powder sample. But you see, in both cases, there is no as such change in the intensity. So a variety of sample can be used. It does not require any specific shape like solids or pellets or powder. You may go for also fiber also, liquid sample also. And another thing, your sample should not be, it's not required that it has to be transparent. You can use also opaque sample in case of lab. That is the problem in case of FDR. The primary restrictions with that the sample hits the sample holder. There is a sample holder and it not degas since the spectra of gases are stronger than those of the solids. For sample containing moisture, this might require oven drying. So before that, if your sample is very much hygroscopic, first you should uh, you kept it in a low humidity chamber or you heat it little bit to remove those moisture using a desiccator and then you put it in a sample holder. So you see if a sample, for example polystyrene, if it is a powder form, still you are getting the intense peak. If it is a seed form, still you are getting the same intense peak. That is the beauty of the photoacoustic spectroscopy. Now what are the significance for composite material? This is the beauty of gas. For composite material or very highly filler loaded polymer matrix, you have no problem to characterize or to the uh, pass analysis. If it is highly opaque or intense color, for example, if somebody is using very high amount of pigment to develop a color sheet, still you cannot do like in case of FTR we need to go for the first to vaporize the matrix, so there may be chance of degradation and then from there what will be the the liquid portion, you have to uh, check that liquid part. But here you don't go for any solvent or any other specific sample preparation process. You just put the sample, you will get the data. The next important thing is the quantitative analysis. You can directly analyze that how much percentage of some element is present in your matrix. The third point is very much important. We will discuss how it is it check the depth profiling also. So surface analysis and depth profiling could be done, and determination of orientation function of polymer also possible through the patch analysis. So how it could be done? It is done actually by modulating the frequency. So here is that chopper. So by fixing the rotation, you can do the depth profile analysis. Now, how it can be done? The quantitative analysis, for example, it is a fast spectra of a nitrile butadiene rubber. Let's say if you are purchasing NBR from different supplier and they have different acrylonitrile content, so how you can confirm it that whether the supplier is sending you the same sample or there is the change? You can do the fast analysis. So what you will do, you prepare different you check sample from different supplier. If there is a variation of acrylonitrile content, you just calibrated the graph. In x-axis you put the concentration of acrylonitrile and in y-axis the intensity. From there the known sample, if you calibrate it, you check 3-4 known sample and your unknown sample, you will get the data that how much acrylonitrile content is there. How you can do that? First of all, you know the C triple bond in peak appeared at 2238. That is this one. And NBR is consisting of two different rubber, that is nitrile and butadiene. For butadiene, you will get a peak around 1443, and also there is another significant peak, that is 969. So if you check the area of this curve and area of this curve and then make the ratio of these two, you will get the what is the composition of the acrylonitrile content. The next thing is the if it is a highly fillared composite. For example, you prepare a 4 sample, one is 0%, that is pristine rubber, then you add 10% carbon black, then 20% and 50%. You see there is no as such peak position shifting of the different corresponding peak, and also the signature peak of carbon black you can also get from the this patch analysis. Now it is not up to 30%, even you can go beyond 50-60%. That is very much difficult in case of FTR, because highly loaded sample it is difficult to get the FTR spectra. But in case of patch, since it is not the absorption technique, it is emission, so there is no as such difficulties if it is a highly loaded matrix. So we have also told that the advantage or significance of patch is it can do both surface analysis and depth profiling. How it can do that? So first, D is the thickness of the sample. D0 is the optical absorption length, or OBL, that is the distance the infrared radiation can travel through the sample, that how much thick to how much distance radiation can travel from the surface to bulk. Equal to the 1 by beta, where beta is the optical absorption coefficient, that is the inherent property of a sample. And dt is the thermal diffusion length, that is the distance the thermal wave can travel through the sample. Now there are 4 different terms. So optically transparent means if d0 is greater than d, the optical absorption coefficient is small, so that is optically transparent. Optically opaque means what? If d0, that is the thickness of the sample, is less than the d, d0 is the optical absorption length. If it is less than the d, the thickness of the sample, it is optically opaque. That means the light is fully cannot pass through your material if the sample thickness is very much high. And thermally transparent means if the thermal heat capacity and conductivity of the material is very much high, and the dt, the thermal diffusion length, that a distance traveled from the surface, if dt is less than d, it is thermally thick, and if dt is greater than d, that is thermally thin. Now, in case the signal intensity would be proportional to the product of the optical absorption coefficient, that is beta, and the thermal diffusivity coefficient, and so it 3 by 2 depends on the modulation frequency. So by varying the modulation frequency, that means the speed of the chopper, you can simulate that dt or do or dt. Now W, that is the frequency, equal to twice pi into OPT, and that is equal to also 4 pi into the mirror velocity. Now OPT is the optical path difference. So that omega, that is the modulation frequency, that means how that is the speed of the chopper, that is equal to twice pi into OPT and 4 pi into mirror velocity. Now if dt equal to 2 alpha by omega whole to the power half, where omega, that is the frequency of the modulator, is 4 pi into mirror velocity, and dt equal to 2 alpha, that is alpha, it is the thermal diffusivity, divided by 4 pi into mirror velocity. So the depth being sampled, that is you are checking the depth or you are doing the depth profiling, you can tune just by modulating the speed of the chopper, and that is obviously that thermal diffusivity coefficient, that is alpha, equal to thermal conductivity divided by rho into heat capacity. So if you increase the speed, then the mm, depth analyzing part will be small, so it will be much more surface oriented. If the speed is low, that will be vice versa. Now thermal diffusivity of polymers are different because that is obviously inherent property of a material. For example, polyethylene, that is highly dense, so it has thermal diffusivity is a 2.3 into 10 to the power minus 3 centimeter square per second. Now polychloroprene, it has a very low thermal diffusivity, that is 0.68. Now higher the thermal diffusivity, more will be the bulk information, because as from here dt, if dt is greater than d, so thermal conductivity, if it is large, that wave can generate from the bulk of your material. So that's what you can do the depth profiling of your sample. So it is not only surface based, from the bulk part also you will get the information. Now how in real case how it works actually, let's for example a composite, it has a zinc stearate, because we used to add a zinc stearate at a accelerator activator. Now with time we know that zinc stearate can bloom from the bulk up to the surface. So with time zinc stearate can bloom from the bulk material to the surface. Now by varying the speed of your chopper, you can study the surface property also. So when there is a zinc stearate, if you plot a specific peak position, that is 1539 versus mirror velocity, so you will get that with time the surface, if you go from here to here, that means you are getting more data from the surface only. So if the peak intensity is higher, so that means higher is the presence of zinc stearate on the surface. If you uh, do this plot, that is IR band ratio 1539 by 966, and in x-axis, that is mirror velocity with decreasing the depth, and here it is the increasing zinc stearate concentration. So by modulating the chopper speed, you can get much more data from the surface. Now if there is a higher amount of presence of zinc stearate, you will get this ratio will be high. In that way it can do the quantitative analysis part. Another example is, for example, we know that for ozone resistance purpose we use the CP wax. Now there is a presence of carbonyl obviously, and similarly if you do the test with time, that how much presence of wax on the surface, whether it is deteriorating or not, you do the patch test, and if you are getting that higher amount of ratio, that means still it has a good amount of ozone resistance. So in that way, it is through the quantitative analysis, just by modulating the speed of the chopper. Now, how you can determine the orientation function of a polymeric material? Orientation means if you are doing, somebody is doing extrusion, or uh, when it is forming the fiber, so there is obviously the orientation of the polymeric chain. Now, how it can determine that? In order to determine the orientation effect in polymers or blends or composite, usually extrusion or injection molding required. Now, a polarized pass is essential for that part. For polarization of ion radiation, you need a polarizer. So we'll discuss in later in optical microscopy what is polarizer. Just for your information, there is a polarizer used KRS5 wire grid that is inserted immediately in front of your the cell, and without any special preparation, polarized pH can be directly applied to the polymer granules or polymer blocks. In this way, the preferred orientation given by the machine axis, or if you stretch a rubbery type of material and you are doing that patch analysis, you can get the knowledge about the orientation of the polymeric chain inside the material. Now, next is very important, Raman spectroscopy. The one and only Indian scientist who won the Nobel Prize in 1930, and also who worked in India, basically in Calcutta. Now, before going to the details about Raman spectroscopy, the common term we need to know that if a light falls on a substrate, what are the different physical changes or process occurred. So first is the reflection. That means the light incident in a specific angle on a substrate, and it is reflecting at a same angle. The next is the transmission. That is the how much fraction of the incident light of a particular wavelength transmits through the sample from one side to another side. The next is absorption. That is the fraction of the incident radiation absorbed by the material. And the fourth one is the scattering. That is measured the amount of light that substance scattered from its surface. So these are the four phenomena happens when a light is falls on a material. Now, what is Raman spectroscopy? So it is a non-destructive chemical analysis technique which provides detailed information about the structural fingerprint by which molecules can be identified. So from FTR, you can know the structural part to get the insight about the structural part of a molecule. What are the functional group present on a molecule? Similarly, from the Raman, you can identify the molecular structure and presence of different functional group uh, in the material. So it determines vibrational modes of molecule, although rotational and other low frequency mode of system may also be observed from the Raman spectroscopy. Now, as CV Raman, the quad spectrograph measured the wavelength of scattered light that known as the famous Raman effect. Now, what is the fundamental principle behind the Raman spectroscopy? So, there are basically two theory. One is the classical theory, and another one is the quantum theory. From both classical theory and quantum theory, we can understand the how Raman scattering happened and how actually uh, we can determine structure or how it works. So to understand the classical theory, first we need to know polarizability. We'll discuss polarizability, then different types of polarization and polarization ellipsoid. And to know the quantum theory, from the quantum theory, we can also explain thermal spectroscopy. For that, we need to know the elastic collision and inelastic collision. First, we will discuss about the polarizability. Now, from where the term is coming, obviously, there is a polarization. Then only polarizability will come. So, polarizability usually refers a tendency of a matter when, in the presence of an electric field, it acquires electrical dipole moment in proportion with the strength of the applied field. And it is not the inherent property of the matter. Basically, it is a transient property. So, if you remove the source of the electric field, there will be no polarization. Whenever it is under the electric field, there will be the polarization. And that uh, uh, the strength of polarization, it depends both the material and also the strength of the electric field present. Now, it is the property of all matter, considering that matter is made of elementary particle like electron, neutron or proton. When subject to electric field, the negatively charged electron and positively charged uh, atomic nuclei are subjected to opposite force and undergo charge separation. So, from this cartoon, you can understand, we know that in nucleus there is proton and neutron. Now, proton has positive charge, neutron has no charge. And outside the nucleus, in orbit, there is presence of electron. Now, when there is a presence of electric field, there will be the separation of these two different charge, positive charge and negative charge. Now, electric polarizability is the relative tendency of a charge distribution, like the electron cloud. Since we know that electron is not particle, it has the wave nature, and we cannot determine the fixed position of an electron. That's why it is a cloud of an atom to be distorted from its normal shape when it is under an external electric field. The main funda is, in presence of electric field, the charge distribution will not be homogeneous. There will be a separation or change in the distribution based on the electric field direction and as well as electric field strength. Now, specifically, there are four different types of polarization can happen in a molecule. First is electronic polarization, that is the electron cloud distorted in presence of electric field. The next is ionic polarization. What is ionic polarization? It is the distortion of the charge center. So, atomic polarization arises because there is a relative change in the mean position of the atomic nuclei within the molecule, and these generally uh, observed because the strength of this polarization is very weak and it is observed at a radio frequency level. So, if it is a nuclei, so it is always fluctuating, and based on that, the mean position, it will change in presence of the electric field. The third one is the dipolar or orientation polarization. Now, we know if there is a two heteronuclear atom, so obviously because of the electronegativity difference, there is always delta plus and delta minus charge. Now, in absence of an electric field, they are usually distributed randomly. But whenever there is a presence of electric field, the positive and negative charge will take a specific orientation, and because of that orientation, there will be the generation of a polarization. Fourth one is the interfacial, that is very much important because it actually property of a composite type of material. Now, whenever there is a composite, so obviously there is an interface. Now, when there is an interface, there will be different charge distribution on the two surfaces. So, since there is two surfaces, so obviously the charge distribution will be different in two surfaces. And when there is electric field, so in each surface there will be the orientation of the different charge. In that way, it will generate the interfacial polarization. Now, they have their different strength, like electronic polarization, ionic polarization, dipolar and interfacial. They have their own strength and uh, If you plot log frequency, so you see the electronic is very much high, around 10 to the power 14, 16. Then ionic, and after that the orientation. The most uh, important, the interfacial or interfacial polarization that come in the level of 10 to the power 2. Now, what is the polarization ellipsoid? Now, polarization ellipsoid, if you consider a charge sphere in presence of electric field, it is not exactly sphere, it is now suppressed, or it can uh, take the geometry of a ellipse. So basically the negative and positive charge are polarized in two different directions. So in general, a polarizability ellipsoid is defined as a three-dimensional surface whose distance from the electrical center of the molecule is inversely proportional to the square root of the polarizability along the line joining the point of the ellipsoid within the electrical center, and mathematically you can express that mu equal to alpha into E. The size of the induced dipole, here mu is the dipole, alpha is the polarizability, and E is the electrical field strength. The size of the induced dipole depends both on the magnitude of the applied electric field, that is E, and on the ease with which the molecule can be distorted. And polarizability is anisotropic. Now, the polarizability of a molecule various direction is conventionally represented by drawing polarizability ellipsoid. For example, if you take the hydrogen molecule, it is hydrogen and hydrogen. If you, in presence of electric field, now there is a formation of ellipsoid structure based on the charge distribution. Now, in major axis, where the polarizability is least, the axis of ellipsoid is maximum, and in minor axis, where polarizability is maximum, that is the minimum axis of the ellipse, and that actually also depends in which direction the electric field is working, because as it is a vector property. Now here there is two different molecule, one is the carbon dioxide and another one is the H2. So how polarizability change? Since it is a linear molecule, so initially there is a alpha 0. Now when it is stretching or it is constructing, so in this way the polarizability change. If it is a symmetric stretching, the intensity of the polarizability will be different in different direction. If it is asymmetric, there will be the least amount of polarizability will occur. But in case of H2O, there is also, if it is asymmetric, you see the intensity of the polarizability is low. If it is asymmetric, it is the high. Now, how that, before going to the discuss about CO2 and H2O details about Raman, the next theory, that is quantum theory, we will discuss. So from quantum mechanics, we can also explain the Raman effect. Now from quantum theory, we can consider the incident light of frequency nu as a stream of particles or photon. Each of photon has energy equal to h nu, which is the Planck's constant. Now these photons will undergo the collision with your material. Now if the collision is elastic, that means the total h nu energy will be transferred to the material molecule. So your the incident photon energy h nu will be totally transferred to the material. There will be either full exchange, otherwise no exchange. If there is a inelastic collision, so this elastic collision will generate the Rayleigh scattering. And if there is an inelastic collision, that means the same amount of energy is not transferred. So there may be the energy lost through heat or something else. Then there will be the two different observation. One is the Stokes and another is anti-Stokes. So in case of Rayleigh, so if each new amount of energy is transferred, so the electron will go to the excited state and again it will come to the ground state. So since it is the same amount of energy, then the frequency of the emitted radiation will also remain same as the incident radiation. But in case of Stokes, it will be little bit lower. In case of anti-Stokes, it will be little bit higher. The emitted frequency of the radiation will be higher. Now, what is Raman scattering? Now, when light is scattered by a molecule, the oscillating electromagnetic field of a photon induces a polarization of the molecular electron cloud. This leaves the molecule in a higher energy state. The energy of the photon transferred to the molecule, this can be considered as the formation of very short-lived complex between the photon and molecule, which is commonly called the virtual state of the molecule. The virtual state is not stable, so obviously if it is in excited state, it will again come down to the ground state. Now, how it can come down? For that, it need to emit the excess energy. Now, what is the excess energy? The amount of photon that irradiated on the material, that is h nu. Now, when it is releasing energy through emission, what are the different frequency of the emitted radiation, that you need to know. If it is the same frequency, this scattering will be called the Rayleigh scattering. If the emitted radiation has different frequency, there is two different scattering. One is the Stokes. If it has the radiation frequency is lesser than the incident frequency, that is nu 0. If it has a higher frequency, that is nu 0 plus nu, it is called the anti-Stokes. Is it clear here? What is Rayleigh, what is Stokes, and what is anti-Stokes? Okay. And here it is showing the rotational Raman spectroscopy. So we already discussed during FPR, there is vibrational degrees of freedom, rotational degrees of freedom, and translational degrees of freedom. Now, in case of rotation, there is different energy state. Okay. Now, the energy level of a linear molecule, for example, CO2, the epsilon j will be equal to B into J into J plus 1. J is the a quantum number minus d J square J plus 1 whole square centimeter inverse, and J can be 0, 1, 2, 3. Now, we can reduce it by ignoring this part, since J has a very low value, D has a very low value, we can consider as a B into J into J plus 1. Now, selection rule is del J equal to 0 or plus minus 2. It means either it can Stokes or it can be plus minus 2. Now, here it is showing different rotational energy level of an electron. Now, when del J is 0, you are getting the Rayleigh line. That means same frequency. If it is plus 2, then it will be the anti-Stokes. If it is minus 2, it will be Stokes. Now, usually, to get anti-Stokes lines, the probability is very much low, since for that, the transition should take place from the higher excited ground state to here. It should go from higher energy level ground state to excited state. It is not from the 0, it is happening from 1. Now, since the population density in 1 is usually less compared to nu equal to 0, that's why the anti-Stokes lines usually come at a very low intensity. So, this is the energy diagram. So, in x-axis there is internuclear separation, and here it is potential energy. So, they are the different level, energy level by specific quantum number. This is the lower electronic state or ground electronic state, and this is upper electronic state. Now in case of Raman, since the rotational level is changing, so from here it is coming here. So that is the excited state and this is the ground state. Now when it is coming back again from here to here, when if it is come nu equal to 1 to nu equal to 1, sorry, nu equal to 0 to nu equal to 0, that is Rayleigh. If the electron excited from 0 to 1 and if it comes up to 1, so that is called the Stokes. If it is if it the jump can take place from nu equal to 1 to nu equal to 1 and it comes here nu equal to 0, that is called the anti-Stokes. Yeah. There is also vibrational Raman spectroscopy. So we have discussed the rotational, now it is vibrational. In case of vibrational mode, the equation we can write like that way: epsilon equal to omega e into nu plus half minus omega e xc nu plus half whole square. Now omega is the equilibrium vibration frequency and x is the enharmonic constant. So we have discussed during FPR the harmonic, simple harmonic oscillator. Now if it is enharmonic, usually there remain always enharmonicity, so that's why you add extra term, that is xc, and here delta nu after quantum analysis the solution is delta nu could take these values 0 plus minus 1 or plus minus 2. Now if delta nu equal to 0, that means it is Rayleigh scattering. If it is plus minus 1, that is called Stokes or anti-Stokes. If it is plus minus 2, that is called the overflow. That means it is not excited from ground state 0 to 1, it is going from 0 to 2 on the second excited state, you may call it. And another thing, that is delta E hot, that means it is not excited from the nu equal to 0, rather than it is excited from higher ground level energy state nu equal to 1 to nu equal to 2. So nu fundamental equal to nu excited plus minus delta epsilon fundamental. So here selection rule is 0, plus minus 1 or plus minus 2. That means these are the energy state where only electron can or transition can possible. Now the selection rule in Raman spectroscopy, the primary selection rule that the molecule would be polarizable. It must not have a permanent dipole moment, but it must be polarizable in presence of electric field. That is the first principle to be a Raman activity. Now the polarizability of the molecule tells us about how hard or how much easy it is for an electric field to distort the charge distribution or electron cloud. An atom in which the electron cloud is further away from the nucleus has a large polarizability than the atom where the electron cloud is closer to nucleus. Why? Because we know that those electrons are close to nucleus, they are much tightly bonded. Those are far from the nucleus, they are labile and weakly bonded. That's why the electron cloud which are far away, those are easily polarizable in presence of electric field. Now the symmetric vibration usually give strong Raman signal and no FTR signal. We will discuss in later slide. And asymmetric vibration lead to much weaker Raman signal and are often quite strong IR. Now why it happens? From here you can understand that if it is symmetric, you see the change in the polarizability is very strong, rather than if it is asymmetric, the change in polarizability is weaker. That's why where the polarizability change is higher, you will get high intense Raman line or Raman scattering. Bending vibration mode lead to much weaker Raman signal and they are strong in case of IR spectroscopy. The last one, a molecule can have both IR and Raman are positive at the same frequency, though if the Raman signal is strong, the corresponding IR will be weak or vice versa. So if it is strong IR, the Raman signal will be weak. If you are getting a weak intense peak in IR, you will get strong intense peak in Raman. So this is the summarization. If a molecule has a center of symmetry means like CO2. In that is in middle there is carbon, and at the same distance there is two oxygen. So it has a center of symmetry. If a molecule has center of symmetry, the Raman active vibration and infrared will be vice versa. That means if it is a Raman active, it will be IR inactive. If it is Raman inactive, it will be IR active. And so in case of bending, if it is Raman inactive, it will IR active. Now why it happens? You understand that in case of linear, if it is a symmetrical stretching, so ultimately the dipole moment is 0. But we know that in case of FDR, the molecule must have a permanent dipole moment. But since in case of Raman, the molecule need not to have a permanent dipole moment, only there must be a change in the polarizability. So it will be not Raman inactive. It will show the Raman spectra. Is it clear here? Now, why the linear molecule show this difference in case of Raman and infrared? Nair sir, it is clear na why it is showing Raman active and IR inactive? Yes, yes, exactly, classical theory. So just understand, sir, that we know we have discussed that for FAR that the molecule must be polar. That's why we did not get H2 or carbon dioxide in FAR analysis. We will not get any peak because those are not polar. Those are non-polar, right? Now CO2, since there is a carbon and it is CO2, we know that CO2 has a linear structure. So there is one oxygen here and another oxygen is here. Now we know dipole moment is a vector quantity. So one vector from through this direction from carbon to oxygen, and since there is another oxygen, so there will be another dipole that is towards from this carbon to this direction. So since these are two different directions, so they are ultimately cancelling each other. That's why CO2 is not polar. Now since it is not polar, the dipole moment is 0. Now since dipole moment is 0, it cannot be IR active. Okay. Now in case of Raman, the main important thing is it must not have any permanent dipole moment. Just only polarizability it will change. Now polarizability can change for any material in presence of electric field. So that's why the thing is that if it is Raman active, it will be inactive. But this is only for symmetric stretching and linear molecule. It's not for all type of molecule. Only linear, yes. Now on the basis of understanding Raman and IR, what are the difference? So based on interaction, first infrared is absorption, but Raman is scattering. The next on the based on excitation, it is polychromatic, but here you need a monochromatic. And based on frequency measurement, it is absolute, but in case of Raman, that is relative for anti-Stokes or Stokes. And activity, that is change in dipole moment, must not be 0, but in case of Raman, the change in polarizability must not be 0. Whether it has a permanent dipole moment or not, that is not important. The change in polarizability must not be 0. But in case of FTR, the change in dipole moment, that means it must have a permanent dipole moment or polar molecule. Now what is the Raman shift? The Raman shift is the energy difference between the incident laser. Actually in case of Raman, you need a laser source, for example 532 nanometer single wavelength light. So in Raman shift, the difference between the incident laser light and the scattered light. So the frequency of the incident light and frequency of the scattered light. The difference between them is uh, this difference is the only connected to the energetic properties of the molecular vibration, and that is studied here in Raman. And hence, independent of the laser wavelength, the Raman shift is usually expressed in wave number, that is similar in case of FTR also. So this is the intensity and this is the Raman shift, and usually you will get almost at the same wave number. For example, if carbonyl peak in FTR is coming 1720, in Raman you will also get a peak in 1720 centimeter inverse. Now it is not the wave number. Instead of wave number, what we usually plot in FTR, here in case of Raman, this is Raman shift. Now what are the different application area of Raman spectroscopy? First of all, it is very important in case of carbonaceous material. Now we know there are recent past different carbonaceous novel material already discovered. For example, single wall carbon nanotube. Now we know that CNT is very much costly material, and if it is single walled, that is very much cost. Now whether it is a single walled or multi walled, you can get insight from the Raman spectroscopy. The purity of the carbon nanotube, whether it is defective, whether there is a presence of oxygen, or it has a sp3 type of carbon, you also get that information from Raman spectroscopy. Electrical properties, we know that depends very much on the purity of your nanotube, the number of sp2 hybridized carbon and sp3 hybridized carbon. So electrical properties from the Raman spectra, you can also say that what will be the electrical property of the material. You can compare. If two different CNT has two different peak intensity, from there you can correlate that what will be the best or suitable for electrical application. Diamond like carbon in coating properties, defect or disorder analysis in carbonaceous material, and obviously in case of graphene you must have to go for the Raman spectroscopy. Irrespective of carbonaceous material, there are others different applications, for example pharmaceuticals and cosmetics, geology, life science, for example to know the structure of a protein, and also in semiconductor there is a huge application of Raman spectroscopy. Now why it is important in carbonaceous type of material? So there is two different terms. I don't know whether you heard or not. In case of graphene or CNT or any 2D type of material, there is D band and G band. Now what is D band? D band is caused by the disordered structure of graphene. So we know in graphene there is a sp2, all carbon are sp2 hybridized. Now the presence of disorder in sp2 hybridized carbon system results in resonance Raman spectra, and thus makes this one of the most sensitive technique to characterize the disorder in sp2 carbon that usually come at 1350 centimeter inverse. The D peak is due to the breathing mode of the sp2 rings. So in case of these green are all sp2 hybridized carbon. If all are stretched in a similar direction, and in case of G band, that is arises from the stretching of the carbon-carbon bond in graphitic type of material, and is common for all sp2 hybridized carbon material. And G band usually observed at 1583. So whenever you are going for the testing of graphene or 2D type of material where carbon are sp2 hybridized, you will usually get two peak. One is around 1350, that is corresponding to D band. Another is around 1500 centimeter inverse, that is corresponding to G band. Now except D band and G band, there is also another peak that is called 2D band observed around 2800 centimeter inverse. Now why this band coming at 2500 to 2800 centimeter inverse? That is combined with the G band. This spectrum is a Raman signature of graphitic sp2 hybridized material, and 2D band is a second order two photon process and exhibits a strong frequency dependence on the excitation laser energy. Another important thing from here, we should calculate the ratio of D band and G band. So intensity of the D band and by G band, that ultimately allow you to estimate the defects present in your graphene type of material. If it is higher, D band by G band intensity ratio, so that is the defects is higher. If it is low, so that graphene is much more pure or defect free. Now, what are the advantages of Raman spectroscopy? So, detailed chemical and molecular analysis you can do through Raman, and it can be used to fully characterize your material composition and very fast identification of unknown material. You don't need to prepare a sample in a specific uh, I mean, you can just put your sample. You don't need to prepare your sample. Just put sample and you can do the study. More information about the crystallinity and polymorphism and also phase. So Raman spectroscopy provides information such as crystallinity, intrinsic stress or strain, protein folding and hydrogen bonding. Raman is very fast, and also you don't need to prepare your sample in a specific manner. So that's why sample preparation is very easy, and very important thing is it is non-destructive. So if you put your sample, you can again use your sample without uh, any problem. And also it is not uh, contacted with any other type of substrate material. The third one is atomic absorption spectroscopy. So what does it mean? Atomic absorption spectroscopy. So obviously there must be formation of atom, and it is a emissions type of spectroscopy. So AAS, yes, yeah, D band and G band. Yes, 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 more defect. Yes, higher, higher. Huh. Yes, here less than one. Yes. No, no, it's not. ID by IG. That means if you make ratio of this intensity of this peak and this peak, the lowest is the ratio, higher is the purity. If it is close to 1 and if you are getting zero point 0.5, so obviously zero point 0.5 is much more pure compared to your 1. Huh. So it may be zero point 0.1, it may be zero point 0.2, it may be 1. If it is 1, that means much more poorer performance, much more defective. If it is zero point 0.1, that is less defective. Zero point 0.1 is best, of course. And if you say if you say if it is equal to 1, but still it is higher than zero point 0.1. Yes, yes, yes. That height of that peak, the higher the difference between the height of these two peaks, higher will be the purity. So in case of AAS or AES, that is atomic absorption spectroscopy and atomic emission spectroscopy. So one is based on absorption and another is emission. And for that you must go for the generation of or formation of atom. Yes, it is a analytical procedure for the quantitative determination of the chemical composition by free atoms in the gaseous state, and atom absorption spectroscopy is based on absorptions of light by free metallic ion. So what does it mean? You first atomize the material to the atomic level to form different atoms, and then you check the absorption property of that free metallic ion. In 1957, Sir Alan Walsh discovered this, and also uh, he made it a commercial level in 1957. Now, what is the principle? First, the sample is atomized in either a flame or a graphitic furnace in different way. Actually, there are 4 or 5 different way to atomize the sample or material, and after the atomization, the free atom are then exposed to the light. So first, you atomize the sample, and then you exposed with the radiation, and typically produced by a hollow cathode lamp to, to for the incident radiation, and that undergo electronic transition from the ground state to the excited electronic state. Every element absorb radiation of a fixed wavelength, so each element have their characteristic feature to absorb a fixed wavelength of light, and based on that actually you can disintegrate different atoms present in your material. A monochromator is placed between the sample and the detector to reduce the background interference. From here, the detector measures the intensity of the beam of the light and converts it to the absorption data. So here it is the wavelength, here is the integrated absorbance based on different atoms. There will be the presence of different wavelength of light. So there are flame atomizer, there are electrothermal atomizer, glow discharge atomizer, hydride atomizer, and cold vapor atomizer. So these are the 5 different techniques to atomize your sample. Now, what is the inductively coupled plasma spectroscopy or ICP? So this is actually uh, in a combination of ICP is 2 different spectroscopy. One is AES, atomic emission, and another is optical emission spectroscopy, that is OES. So this is also used to determine the chemical composition or presence of different chemical elements in a substrate material. So there are 2 types: inductively coupled plasma optical emission spectroscopy and inductively coupled plasma mass spectroscopy. So this is the cartoon to show how actually it works. So from here the sample is going, and here is the argon, flow of argon, and here atomization takes place to form the atom, and to do that there is obviously need quartz tube in both side, and there is induction coil, and after forming the plasma there will be the emission disk. Now determination of different composition present in your matrix, how you can do that? So if it in rubber there are different elements present, through ICP OES, if there is a presence of magnesium or silicon, so must be after oxidation there will be the formation of the oxide in ash. So inorganic material or inorganic, if there is a presence of inorganic element, ultimately there will be the formation of ash. Now when there is a formation of ash, you can do those ICP test, and you will get quantitatively how much weight percentage of present of different element. If it is a silica field, there is also chance of Si based salt or calcium and iron, and also you will get the, after doing the ICP-OES analysis, how much percentage present. We'll today we'll just uh, discuss in 1 2 slide, but in next class we will discuss more about electron spin resonance or electron paramagnetic resonance spectroscopy. What actually do here? So this is a magnetic resonance technique which detects the resonance transition between 2 energy state of unpaired electron. But here instead of electric field you have to provide a magnetic field. Now why you provide magnetic field? Because we know any charge species when it is moving, that will also generate magnetic field. Now, since electron is a charged species, and when electron is moving, so it will also generate a magnetic field. Now, the electron has a spin which gives its magnetic moment, that is mu. The magnetic moment makes the electron behave like a teeny bar magnet. So, any charged species will also act as a teeny bar magnet. Now, when we apply the external magnetic field with strength B, the paramagnetic electron can either orient in a direction parallel or anti-parallel to the direction of the applied magnetic field. Since applied magnetic field has a vector quantity, when the unpaired electron is moving around and there are different number of unpaired electrons, so few electron will uh, orient in the direction of the applied field and few will orient in the opposite direction of the applied field. So there is a splitting. Now, electric fields are created by the static charge object and magnetic fields created by the moving charge object. Since electron is moving, that's why magnetic field is generated. Now, when there is the orientation in parallel and antiparallel direction, in that way it is generating the splitting of the electron. Now, how the ESR, the origin of the ESR or EPR? So, magnetic moment of the molecule is primarily contributed by the unpaired electron. So, first of all, the element must have some unpaired electron. Now, the spin magnetic moment equal to root over s into s plus 1 into h by twice pi. Now, what is the s? S is the spin quantum number and h is the Planck's constant. Ms is the total spin angular moment. In the z direction, the component of the total spin will be assume two values, either plus or minus, and it is equal to ms into h by 2 pi. Now, the term 2s plus 1 has different values, that is plus s to minus s. For a single unpaired electron, only two values are possible, that based on the direction, whether it is clockwise or anti-clockwise, based on the there are two spin quantum number, that is either plus r or minus r. And the term ms have a total 2s plus 1 different values. Okay, so s is the spin quantum number and 2s plus 1 the different values ms can take, and that is actually plus s to minus s. So, if you check that plus s to minus s will be equal to total 2s plus 1 different states. Now, if it is a single unpaired electron, only two value, that is plus up, either plus up or minus up. And the magnetic moment mu is directly proportional to the spin angular momentum of any, and one may therefore write that magnetic moment mu e equal to minus Ge into mu b into ms. Thus, why this negative sign? Because the magnetic momentum of electron is collinear but antiparallel to the spin itself. And the term Ge mu b, that is actually this G is called the magneto-gyric ratio. That means the ratio of the magnetic moment to its angular momentum. Since the electron is a charged species, it is spinning as well as it is also like the how the earth is moving around the sun. So earth itself is spinning as well as it is moving around the sun. Similarly, that electron, that is charged species, spinning surrounding its own axis as well as surrounding the nucleus. So it has angular momentum as well as it has also a magnetic moment. Based on these two terms, this it's actually relates these two different momentum, that is magnetic momentum and angular momentum, and the product of G and mu b is related to the magneto-gyric ratio. Now, when there is a presence of external magnetic field, there will be the orientation. So, few electron will orient in the direction of the magnetic field, few will in the opposite of magnetic field. So, in that way, there are two different uh, state. So the Bohr magneton mu b, that is the unit, is the magnetic moment for 1 unit of quantum mechanical angular momentum, that is equal to EH by 4 pi me, where E is the electron charge, me is the mass of the electron, and factor G is the 3 electron G factor, that is a physical constant. Now these magnetic moment interact with the applied magnetic field. So first of all, that because of the presence of unpaired electron, it is generating some magnetic field. Now that magnetic field interact, if you apply some external magnetic field, that generated magnetic field based on the unpaired electron will interact with your applied magnetic field. When it is interacting with your applied magnetic field, there will be a splitting take place. Based on that, you should provide now radiation, that is equal to h nu. If it is equal to the energy gap between these two, the electron will excite to the upper energy state. So today it is to the origin of the ESR. From next class we will again discuss we will start from the ESR basically. So today we are discussed about up to the origin of ESR and how actually electroparamagnetic resonance and electrospin resonance originate from the atomic level, and next Saturday we'll start again from here and we'll go in depth study of PPR. So now sir, you have any doubt? Yes sir, we will discuss in next Saturday also. Actually it is much more quantum mechanical aspect, that how actually magnetic moment generate. So that is actually a vast syllabus, that how it generate on the origin of magnetic moment and all. Anyway, you may just check in Google also if you have interest, that how the magnetic moment generate in electrode or any element, because there are three different uh, magnetic properties. One is diamagnetic and paramagnetic and ferromagnetic. So those three term actually depends on the based on number of unpaired electron and how it generate the magnetic momentum. So here I have set few questions about Raman and Pass. So first one is the criteria to be used as a inert atmosphere for photoacoustic spectroscopy are. So we know, we have discussed that inert atmosphere is required, and that's why we have also discussed why helium is important rather than nitrogen. Now what are the criteria of that inert gas to have, so that it will be best suitable for the gas? So first option is low thermal conductivity and high heat capacity. The second option is high thermal conductivity and low heat capacity. Third one is high thermal conductivity and high heat capacity, and the next one is low thermal conductivity and low heat capacity. So among the four, what is the best criteria? Yes, sir. D. D for the rate. But sir, we have discussed helium. Why we use helium? Because whatever the after uh, interacting with the radiation, your sample will generate and heat. That heat will pass through the gaseous molecule. Now, when gaseous molecules are interacting with that heat, it should convert response immediately. So the option is high thermal conductivity and less heat capacity. Until and unless it is very highly conductive, it cannot pass through. Right now, that's why helium has very high thermal conductivity and very low heat capacity. Very low heat capacity means it is not absorbing the heat, it is passing through the heat. That's why we go for helium rather than nitrogen. Mm. Now next is, which of the following statement is or are correct? The sample for photoacoustic spectroscopy has to be transparent film. Is it correct? First option, the sample of photoacoustic spectroscopy has to be transparent film. Whether there is any requirement for pass that your material has to be transparent? No, you can use any material. Nitrogen is preferred over helium as a inert atmosphere in pass. Just I have already told you that nitrogen is not preferred, helium actually preferred. Now third is, styrene content of polystyrene can be detected by pass, and fourth is none of the above. Styrene content of polystyrene can be detected by photoacoustic spectroscopy. Correct or incorrect? Styrene content of polystyrene, because in case of polystyrene, it's the inherent, I mean the monomer unit has the styrene. So see, you can detect from pairs, because you can detect also from FTR. It's not the contradictory. For example, if something is blooming the surface or bulk, that is different. But since styrene is present, so obviously from FTR and from pairs, from both you can determine the styrene content. Now next, which of the following statement is incorrect? Okay, so this is from the Raman. Now in inelastic collision, kinetic energy is conserved. It is not correct. In inelastic collision, obviously the kinetic energy will be different. That's why you are getting the Stokes, anti-Stokes, and Rayleigh. Then the change in dipole moment corresponds to Raman active molecule. We have already discussed that it is not dipole moment. So it is because polarizability, you must take care about polarizability. So C option is, change in polarizability correspond to Raman active molecule. So this is actually correct. This is incorrect. The answer is B, because dipole moment, you don't need to change the dipole moment to be Raman active. Only the polarizability must be changed. Okay. So thank you all, and thank you, Nair sir. I think yes. Huh. Okay. 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 No issues, sir. From next week we will try, but actually characterization part you must have a fundamental basic. So otherwise it will be difficult to correlate actually. Anyway, sir, if you have any doubt, you just mail me, or you can message me. So what are the difficulties you face in actually uh, the ESR and Raman is little bit uh, much more quantum side. So more theoretical. So for that, if you go through little bit about the basics, then I think it will be easier for you to absorb. But I will try to my best. Let's see how much I can do. Okay, sir. Uh, thank you. We'll meet next Saturday.